Hey guys, a very good morning. Thank you for joining with us. My name is TN Pradeep Kumar Naidu, and we are here to represent Nikit Engineers, which is into welding from the past 42 years. And the kind of knowledge that we have gained over the past 42 years, we would like to share it with you guys to solve a much complicated problems of welding and simplify the entire process. So let's see what we're going to solve today. So guys, the problem that we are trying to solve today is thermal batteries welding. Basically, what are thermal batteries? Thermal batteries are used for missile launching, and these are very critical for any defense systems. And the type of welding that we are carrying out here is TIG welding, that is tungsten inert gas welding, and the process is fusion, not with wire feeding. So let's go check out how the component looks and the characteristics of the same. So guys, this is how the component looks. The component profile is basically round or circular in shape. It's a deep drawn 304L component, and once it's deep drawn, there's a cap which comes on top of it, which is about 3 to 5 mm in thickness. It has also got about 3 to 5 leads based on your charge, and this component diameter varies right from 40 to 110 dia, and the height of the component doesn't shoot out beyond 200 mm, and the component that you're looking at is a welded component. So why is it so critical that such a component cannot be done manually? We would rather say that yeah, manually we can do welding, but it becomes very critical as the thickness of the shell is 0.5 to 0.65 mm. To merge a 0.65 mm to a 3 mm or a 5 mm cap, it becomes very critical. And the last, not the least, critical stage would be during a weld, the battery is live. So there are chances of explosion. So the right amount of current, the right amount of bead is very essential in welding. And in case you need any kind of support in relation to the component itself, you can have these components delivered or get it done through a company called as RES Batteries. So here's a quick look at how the website looks. Yeah, so these guys are RES Batteries. These are the kind of components that are being welded in our system, and they are located in Hyderabad. Now let's talk about the configuration of the machine. So basically we have a component which is circular in shape, the length is less than 200 mm, and how are we going to weld it? Yeah. So the display that you can see here is on my 3D software, where we've got two main axes that we have designed. One is the rotary unit, which goes up to plus or minus 760 degrees, and the other one being our linear axis, which has a stroke of about 200 mm. So these two axes are very critical in welding the batteries, because with one axis, that is with x-axis, you set the diameter of weld. Let us say you've got a 40 mm diameter, you set 40 mm, and the torch stops exactly at the periphery of the weld bead with a distance or a gap of 1 or 2 mm based on your setting or based on your tungsten. And the tungsten that we have used here is about 2.4 mm, and the current required is between 100 to 200 amps. And the rotary unit, once the torch positions itself near the component, the rotary unit starts rotating the component. There is an initial arc delay, there's an initial pre-flow delay, and then the component starts welding and rotates up to 360 plus an overlap degree of about 10 to 15 degrees, then moves back to its home position. So that's the entire sequence that we have come across this particular process, which is giving us a very good result. Now if you see the kind of fixture that we've designed, there are four types of fixtures depending upon the kind of components that the customer has given us. When we're talking about speeds, the linear axis runs about 30 mm per second, but the rotary axis does give you about 15 to 20 rpm. For a component like this, the maximum rpm required would be in the range of 2 rpm to 8 rpm. because since it's stick welding and it's fusion, you don't run it at very high speeds because the accuracy required is really high. When we talk about maintenance of such a machine, it's a very simple tool because the kind of guideways that we have used here is basically a dryline based guideway from I guess, where there's no frequent maintenance required because they are based on linear bushes, solid bushes without any liquid or without any kind of lubrication required. Then for the rotary unit, yeah, regular greasing or oiling is required. For any systems that we build, there are pros and cons of it. But before getting into pros and cons, let us talk about the fixture material. The kind of material that we've used here is AL6165. Is very good conductor of heat, and the kind of welding that we are doing, there's lots of heat that is being generated on top of each fixture. When we're talking about pros and cons, the biggest advantage in this particular system is it's very economical, and the kind of cons that we see, the speeds are really low because the linear actuator cannot run beyond 30 mm per second, and the rotary axis cannot run beyond about 15 to 20 rpm, and the rotary axis is DC. The linear actuator is again DC. There is no stepper motor or servo motor involved in this, guys. Now moving on to the costing, so for project GL002, thermal batteries welding automation. Now moving on to the costing, guys, for project GL002, that's what we name projects basically. So thermal batteries welding automation, for which we need to check out the costing here. Yeah, control systems with display panel, basically the display is about 3.5 to 4 inch, either touchscreen or type, the control system being Delta. Cost doesn't change, that is $1,230. Linear x-axis is about $425, that is including the actuator and the axis slide system. And rotary axis assembly, that is the third assembly that we are going to talk about, is about $493. It's basically again DC motor based. Now torch and adapter assembly, these are for fixing and positioning of the torch along with the torch of 200 amps water cooled. It can be water cooled or air cooled, but the model that we have used currently is air cooled, and the cost is $185. Then comes to fixture assemblies. We have modeled in 5 different fixtures for 5 different components, and the total cost that we have incurred is about $1,120. And frame and sheet metal, that's the sixth iteration that we're going to talk about. Frame and sheet metal is about $615. Safety system is being at $115. You may also know that all motors are DC and power consumed is hardly about 1150 watt hour. Now the total project BOM cost boils down to $4,183, and the non-inclusive costing as usual will be your labor consisting of design, procurement, inspection, assembly, electrical testing and training. Second being company overheads, it depends on different areas. The third, consumables based on your welding power source, welding wire, gas and tungsten. Fourth one, the kind of power consumption that happens during different phases and different locations. Fifth is the installation cost. Sixth being packing and forwarding. Post this, let's move on to our pictures of how we've designed this machine, the kind of assemblies that get involved, and most of the electrical portion of it. Yeah, so here's a bit. Okay, let's see what is there. Okay, as you can see, there's a tabletop model with a display stand and a display unit, and we have provided a provision. We have in the design, what you can see is all the 5 fixtures can be kept on top of the assembly itself, so that you know which component you are welding currently and what is the next fixture that you need. And here is the look at our electrical wiring system. Basically it's a very old system, so the kind of wiring is pretty bad, but still the kind of systems. but still a whole lot of we have used a whole lot of relays for switching on the DC motors, forward direction, reverse direction, then welding switching on, then there's a Delta PLC here. Looking at the entire layout of the electrical panel box, what you can see is on the top, that is the display face has got the display sequence button, there's an indicating lamp, there's a mushroom switch for emergency stop and start, there's welding on and off, then there is a modulator for speed setting of the actuator, also for speed setting of the rotary unit, then there is welding on and off, forward and backward. And getting inside our control panel box, what we see here is on the first layer we have a whole lot of relays with the PLC and SMPS, and at the second stage we have transformer and our PCB for controlling our rotary unit. So moving on to all the different portions of the machine, here we have the main station, then we have the torch station, the rotary unit here, and then the welded sample that we've been taking trials out. The sensors are basic proximity sensors, and we are looking at yeah, this is the display where we're showing you the main page, which has got about 5 different components, further classifying into what are the power setting, what are the time setting, and what are the delays that you need, and then moving on to your actuator timings and basically the external electrical wiring configuration. The other thing is the most important portion of the entire system. As you've seen, most of the elements in the machine has been covered. Now let's move on to the video that we would like to show how we do the exact welding. So when you switch on the sequence, first the actuator moves into position, and then there is an initial delay, what we call as the position delay, and then the arcing switches on, then the rotary starts rotating for about 360 degrees, plus there's an overlap degree that we have set, and it moves for that particular overlap range, and then the arc cuts off, and then the post flow cuts off. That's how the machine has been configured, and you can see the kind of weld weight that we've been achieving here. It's hardly in between 1 mm to 2 mm weld weight. Now to have a closer look at how the component looks post welding, let's go back to, yeah, here is the component. Yeah, this is the kind of finish that you get, guys. A very thin finish, and this is completely sealed. Even a small gap relatively causes a lot of harm in this and gets rejected. Basically what we are displaying is a smaller component and a bigger component, how it varies and the kind of weld beads that we've given. So coming back to the kind of resources that we are putting out onto our channel for our viewers to see and for our viewers to download and start this project is basically the step file of the entire assembly, the electrical panel wiring system, and the kind of torch that we have used, kind of process that we are setting, and the entire bill of materials. So you can just download it via the link that is mentioned post the video production, guys. And thank you so much. We'll catch you back tomorrow.